Hello everyone. Today I'm going to talk about an example of a possible fossil earthquake in the Naukluft in order to discuss the question, where are all the earthquakes in the rock record? Now, as this map shows, earthquakes are dangerous phenomena that pose a significant threat to population. But most of what we know about earthquakes and earthquake source rocks come from studies that use geophysical methods, surface structures, and lab deformation experiments. And it's challenging to study deep earthquake source rocks on active faults. And so we need to properly study earthquake source rocks. We need to look at ancient faults that are similar to active faults and that have been exhumed, and that we know have experienced earthquakes. So we need to be able to recognize fossil earthquakes in the rock record. And so an earthquake forms due to buildup of stress in the crust that is rapidly released in a pre-existing or the formation of a new fault. And earthquakes are usually associated with around 1 meter a second in terms of slip velocity, which is in contrast to normal slip rates for a creeping plate around 1 to 10 centimeters per year. Now, at earthquake slip rates, rocks become dramatically weaker than they normally are. And that is what this figure over here is showing, where we have friction coefficient on the y-axis and slip rate on the x-axis. And the lower the friction coefficient, the weaker the rock. So these values were obtained experimentally, and we see that with increasing slip rate, rocks tend to get weaker. And this has been shown to happen by several different mechanisms. So at very high slip rates, weakening is facilitated by friction and melting. And we see evidence for this in the rock record as fault-related pseudotacholites, which are solidified melt veins. In carbonate rocks, decarbonation reactions act as fault weakening mechanisms, and that is what likely happened in the gritty dolomite, which forms the basal thrust of the Naukluft complex. Gelification is something that has been shown to happen at slightly slower but still fast slip rates, where silica gel forms on the fault surface. Now, silica gels have a dynamic weakening effect because they are thixotropic, which means their viscosity decreases with increasing slip rates. And pseudotacholites are still the only direct accepted evidence for fossil earthquakes in rocks. And a big problem that we face with recognizing earthquakes products is that because a fault records all of the accumulated deformation it experiences over time, it is generally very difficult to tell if there have been individual slip events on a fault, and also the rate at which slip has occurred. And so we need to be able to recognize indicators of dynamic weakening in the field in order to distinguish fossil earthquakes from other kinds of deformation. And today I'm going to talk about a potential example of dynamic weakening caused by silica gel in a fault in the Naukluft. Now, interpreting that a silica vein formed by dynamic weakening in a fault is not straightforward. For one, there are multiple natural sources of silica gel, such as hot springs, volcanic vents, epithermal veins associated with volcanic fluids, and even diagenesis of sediments containing biogenic hydrous silica grains. The second problem is that amorphous silica, or opal, is not very stable under normal crustal conditions, and it dehydrates and recrystallizes to quartz even at low green schist facies conditions. However, there are some rare examples of microcrystalline veins in faults that show evidence they were once amorphous silica on a fault surface, such as this example here, which is found the Corona Heights fault in San Francisco. And here, Kirkpatrick et al. Showed that this microcrystalline layer, which we see in this thin section image down here, it has properties that are indicative of it having been a silica gel layer on the fault surface while the fault was active, and they concluded that it facilitated fault weakening during slip. So we found a similar vein in a fault in the Naukluft, in the Åke fault. The Åke fault is found around here, the eastern side of the Naukluft, and over here. And it separates the dolomites and shales of the Bullsfort formation in the hanging wall from the zebra shales in the footwall. And the silica layer is found in 3 locations within a 2-kilometer section on the fault. The locations are shown in white on the map here, and the longest sort of semi-continuous area of the layer is found over a 50-meter stretch over here. At this location, the hanging wall consists of dolomite, and the footwall blue calcareous shales. And the fault zone has a structure such that the shales in the footwall are separated from the silica layer by a dolomite breccia, shown here. The dolomites above the silica layer are less brecciated, but they still have a high fracture density, and all of the shear sense indicators on the fault are consistent with typical top to the southeast shear sense that we find for this area of the Naukluft. The silica layer, when it's present, is always within the fault. It has sharp boundaries and is subplanar, and it's anywhere between 0.5 millimeter and 10 millimeters thick. And it is remarkably continuous along the fault itself. When we look at the silica layer in thin section, we see that it's microcrystalline to cryptocrystalline quartz. The edges of the layer are darker and have isotropic quartz, suggesting that they're finer grained than the core of the layer. And the layer displays a wispy texture that we see in the image here, which we interpret as flow banding. We also find occasional clasts of microcrystalline quartz in the dolomite breccia, suggesting that previous silica layers may have existed. And the layer has a very different microstructure, to the only quartz vein that we found in the area, which I'm showing here. And that quartz vein is much coarser grained. It has an antitextile and blocky texture. Under cathololuminescence, the silica layer shows very unusual colors for quartz. Typical quartz has this bright blue color under Cl, and we see it for that tetraedral grain in the dolomite breccia. The lilac Cl colors for the silica layer are more commonly observed in high temperature igneous quartz or metamorphic quartz grains that have cooled very quickly. So it's a very unusual color. In the scanning electron microscope, we see that the silica layer is porous. There are two different types of pores. We have these very large pores, which we find at grain boundary intersections, and then we have much smaller pores that we find along grain boundaries. And their shape suggests that there has been volume loss by contraction. So for the estimation of porosity, we used image analysis and found it to be around 13%. And the transition from opal CT to quartz by dehydration corresponds to a volume decrease of around 12%. So the porosity that we see in the silica layer may be due to this transition, and that indicates that the layer was most likely once amorphous silica before it recrystallized to quartz. Transmission electron microscopy reveals that the silica layer contains these 100 to 200 micron sized nanospheres, which are not normally found in quartz. Now, when silica solution precipitates opal, it begins by precipitating silica colloids, and once a solution is saturated with colloids, it becomes an amorphous solution. And so we interpret these nanospheres as silica colloids. Now, TEM work also showed that the density of dislocations in the quartz layer is very low, and dislocations build up when a crystal is deformed. So the lack of dislocations in the layer indicates it was recrystallized statically with very little deformation. So now we've established that there are multiple indicators that suggest that the silica layer originally formed as amorphous silica material and subsequently recrystallized to quartz. And this, combined with the structural position of the vein in the fault, suggests that it does indeed represent a record of dynamic weakening, possibly an earthquake. But the question remains, how did the silica layer actually form? In the experiments where the silica gel formed on a slip surface, it formed by grinding comminution and hydration. And this is probably how the Corona Heights silica layer formed, because the wall rocks there are chert. But the silica layer in the other fault is bound on both sides by dolomite that's very poor in silica. And it's difficult to see how the quartz in the wall rock could have concentrated to form the silica layer by comminution. So where does the silica come from? One option is that the silica gel precipitated as a vein during advection along the fault. And this is something that has been suggested along other faults where advection of fluids from higher pressure and temperature conditions to lower pressure and temperature conditions can cause supersaturation and precipitation. To assess the feasibility of this, we calculated the silica solubility in an aqueous solution as a function of temperature and pressure. And for this diagram up here, we plot silica solubility, or the log of silica solubility, K, against depth. And the diagram shows that if silica gel were to precipitate at, say, 1 to 2 kilometers depth, it only requires that fluids migrate a very short way, several hundred meters, in order to change its solubility by enough orders of magnitude to supersaturate the solution. And so it's possible that fluids became supersaturated by migrating from deeper to shallower crustal levels. But we still have to think about the fact that the Åle fault is a fault that dips 20 degrees, so 1 kilometer of vertical transport is equivalent to about 3 kilometers along the fault. And a precipitation of a vein would be limited by how fast a fluid could advect, or how fast a vein could precipitate from a supersaturated fluid. And work in Costa Rica and similar environments show that fluid flow rates that are likely would take millions of years, or at least several 100,000, to precipitate the silica layer at the thickness we see it today. And so it's more likely that quartz veins would grow. But if we decide to assume that the flow of the fluid is not the rate limiting factor, which is possible during an earthquake, then we can examine how long it would actually take a vein to precipitate based on the precipitation rate, given it has an unlimited amount of fluid. And so the diagram down here shows that situation where we have a precipitation rate in meters per second against the degree of saturation of the fluid. And if the degree of saturation is around 10, which is reasonable, then the rate of growth of quartz at 200 degrees Celsius is only several tens of microns per year. And so that's also still too slow if we're talking about fast processes here. And so advection alone is not a viable method to precipitate the silica layer considering the thickness it has today. We can't rule out that advection first led to precipitation of quartz veins that was a slow process and then which were later reworked by slip. A third possibility is that the silica layer formed by on-fault reactions during slip. Now, instead of causing supersaturation by varying pressure and temperature, it's also possible to supersaturate a fluid by chemical changes. And one example is boiling, where separation of the vapor causes the remaining fluid to become supersaturated. Another example is variation in pH, and low pH inhibits the precipitation of quartz and favors the precipitation of hydrosilica. And so the wall rocks, which are dolomitic, are likely to release CO2 during fault slip, and that can lower the pH of the system. A third example, which I show in this diagram here, is the effect of pressure on silica solubility. And for pressures above about 0.2 kilobars, we see that the silica solubility doesn't really vary much with a pressure change. Whereas between 0.1 and 0.2 kilobars, we see a rapid decrease in silica solubility of 4 to 5 orders of magnitude. And this is where flash vaporization happens. So this means that precipitation of silica can happen as fast as micrometers in seconds or minutes. The problem is that the solubility here is still too low to bring in enough silica to produce the thickness of the silica layer with a reasonable volume of fluid. And so the silica layer formed this way, it would have to have done by multiple flash vaporization events that built it incrementally over time. The observation of microcrystalline quartz fragments in the dolomite breccia does support this multiple event idea. And so we think that there are two possibilities for the formation of the silica layer in the Åle fault. The first is that it formed by comminution of a quartz vein that was previously present in the fault and became a gel during the slip event. And the second is that it formed by multiple episodes of flash vaporization during multiple slip events. And the observed layer represents the most recent event. Now, option one is less likely because we only see one quartz vein, and we would expect to see more. And option two is what we're left with, which suggests that multiple earthquakes facilitated the formation of the layer, and that we only see evidence of the most recent event. But regardless of how the silica layer formed, it is still likely to have contributed towards dynamic weakening and represents at least one earthquake on the fault. And so what we've shown here is that deciphering evidence of short-term deformation, like earthquakes, from long-term deformation is challenging, and that evidence of paleoearthquakes is easily destroyed by recrystallization or metamorphism, and the evidence that we do see may be the culmination of multiple earthquake or deformation events. And I think that we have to be careful deciphering the structural relationships, and we have to be able to show, as we have here, that the fault vein represents a slip surface. and that is the key to finding earthquakes in the rock record. Thank you.